Good day, my viewers. I am Legendre Equation. You are welcome to another edition of our class on mathematical method. Today, we shall be discussing an interesting topic, part of special function. The topic is Legendre Equation and polynomials. In our previous classes, we have looked at some special functions and special equations. Among such special functions that we have considered are gamma function, factorial function, and beta function. And among the special differential equation that we have considered is hypergeometric function. Today, we shall be looking at Legendre equation. Legendre equation is, like I said earlier, a special equation as far as mathematics is concerned, and it has a wider range of application in both applied mathematics and other physical sciences. In fact, in engineering, it has a lot of application. So, you are welcome again. Let's start the class. A special equation of the form, a special equation of the form 1 minus s squared y prime prime plus minus 2xy prime plus n into n plus 1y equals to 0. Call this one equation 1. This equation is what we refer to as Legendre equation. And equation 1 can as well be rewritten as d dx of 1 minus s squared y prime plus n into n plus 1 y equals to 0. Equation 2. Why is it so? If you look at this is the differential coefficient, differentiate everything you have within the bracket. If you have to differentiate what we have within the bracket, then what do we have? If this becomes product rule, let us hold this one. We have 1 minus s squared, then differentiate y prime, that gives y prime prime. Then differentiate what we have here. We have minus 2x multiplied by y prime. Then we generate equation 1. And that is that. Now, there are some certain things we need to know as far as equation 1 is concerned. Number 1, it has singularity. It has singularities at s equals to plus or minus 1. 2, it has two linearly independent solutions denoted Pn of x and Qn of x. Number 3, whereas Pn of x is Legendre polynomial of first kind, comma, Q of x, Qn of x is a Legendre polynomial of second kind. So we denoted the two solutions of the equation 1 as Pn of x and Qn of x. And the two solutions are called Legendre polynomial of first kind and the Legendre polynomial of the second kind. Now, the next question we need to ask ourselves is, how do we obtain the value for the two solutions, the Legendre polynomial of first kind and the Legendre polynomial of second kind? Very simple and straightforward. We solve equation 1 at a regular singular point using the method of Frobenius in order to determine the value of the Legendre polynomial Pn of first kind and that Qn of second kind, which are respectively the solution of Legendre equation. So let's look at how to obtain Pn of x and Q of n of x. There are several ways of obtaining this from Frobenius method. So let's take them one after the other, those ones that we can consider today. Now let's consider equation 1 again. 1 minus x squared y prime prime minus 2xy prime plus n into n plus 1y equals 0. Equation 1. Let y equals to summation ar x is power r plus c, r from 0 to infinity. Call this equation 3 since we already have equation 2. We already have equation 2. Let's call this equation 3, and that's our trial solution. So the next thing is to substitute equation 3 in equation 1. Using equation 3 in equation 1, what do we have? We have, let's see what the result will look like. If I differentiate this twice and multiply by 1, I will generate summation r plus c minus 1 ar x is power r plus c minus 2 from 0 to infinity minus the second derivative of y multiplied by s squared results to from 0 to infinity r plus c into r plus c minus 1 ar x is power r plus c, then minus twice summation. Differentiate this one once and multiply by x, we have r plus c ar x is power r plus c plus n into n plus 1 summation ar x is power r plus c, r from 0 to infinity, everything equals 0. Let us be very sure that we have not omitted any terms, like we did explain in our last class, one of our previous classes rather, that before you proceed from here, you need to confirm if all terms are intact. How many times are we expected to have here? 1, 2, 3, 4. 4 times. So we have 1, 2, 3, 4. 4 times. Now, having done this, the next stage now is to look at the powers of x. We have r plus c minus 2 here. We have r plus c at this point. R plus c, r plus c. We have just two powers. R plus c minus 2 and r plus c. Now, let us bring all the common power together under the same summation. Then what do we have? Bring all the same power together under one singular summation. Then we are going to have summation r plus c minus 1 x is power r plus c minus 2 r from 0 to infinity, then minus summation this and this, they have common factor, which is r plus c. I can write that one as r plus c. Let's write it this way. A bigger bracket from 0 to infinity. R plus c, then we are left with r plus c minus 1 here, we are left with plus 2 here. And that will give us r plus c plus 1. Then this is going to be negative because we have factored out a negative. That becomes n into n plus 1. Everything ar x is power r plus c equals to 0. Having done that, what is the next thing to do? Now, if you look at this, the difference between the two powers is 2. So we'll concentrate on the least power and we move that by 2. How do I mean? Evaluate. X is power r plus c minus 2 at r equals to 0 and r equals to 1. By so doing, we are going to have this as c into c minus 1 ar x is power r plus c minus 2 a naught x raised to power c minus 2 plus, substitute 1, we are going to have 1 plus c into c a1 x raised to power c minus 1 plus, by the time we return this one back to 0, we are going to have summation I have r plus c plus 2 r plus c plus 1 a r plus 2 minus r plus c into r plus c plus 1 minus n into n plus 1, everything ar, then x raised to power r plus c equals to 0. That's the expression we are going to left with. After evaluating x raised to power r plus c minus 2 at 0 and 1, we obtain this. Then the counter is already at 2. In order to take this one back to 0, at every point we see r, we replace r by r plus 2 to obtain the expression that I have here. So the next thing, we equate the coefficient. Equate the coefficients. By so doing, for the first time, we are going to assume a naught is not 0, comma, then this implies that c equals to 0 or c equals to 1. And this is what we refer to as initial roots. Let us take the case of c equals to 0. If you substitute c equals to 0 here, of course, for c equals to 0, a1 automatically becomes 0. Because if you put a1 automatically becomes undefined. A1 is undefined because this particular spot will have become 1, this is going to be 0, and the 0 multiplied by everything here is automatically 0. So there is no way A1 can be determined, and that becomes an undefined situation. Then if you put C equals to 1, for C equals to 1, if you substitute 1 here, we have 2, substitute 1 here, we have 1. 1 times 2 multiplied by A1, that implies that my A1 will automatically become 0. That's exactly what we have. Now, the final term, we make the A with highest subscript, the subject of formula. We have R plus 2 here, we have R here. We make AR plus 2 subject formula. By so doing, we have AR plus 2 equals R plus C into R plus C plus 1 minus N minus N into N plus 1, all divided by R plus C plus 2, R plus C plus 1, AR. Let us call this one equation alpha. Equation alpha, from what we have discussed in our previous classes, is referred to as recurrence relation or the quotient formula as far as the solving of the Legendre equation is concerned, in order to obtain the Legendre polynomial of first kind and second kind. Now, you will observe that one of our initial roots actually results to having A1 as being undefined, as not being defined. So in that case, that simply means that the C that make A1 to be undefined will give birth to the two solutions, and that C is C equals to 0. So I will go with C equals to 0 in order to obtain the two solutions. Now, C equals to 0 now. For C equals to 0, AR plus 2 becomes, I have R into R plus 1 minus N into N plus 1, all divided by, I have R plus 1 and R plus 2 AR. Let us factorize the numerator. That gives R squared minus N squared plus R minus N. And that is R minus N into R plus N plus 1. So we have this to be R minus N into R plus N plus 1, all divided by R plus 1 into R plus 2 AR. So let us now make substitution for R. R from 0 to infinity. So when R equals to 0, A naught become arbitrary. So we are going to have A2 equals to, what's our A2? We are going to have A2 to be minus N into N plus 1 divided by 1 multiplied by 2 A naught. Let's take the remaining one. r plus 2. Let's take a3 for instance. a3 becomes, substitute 1 for r. We're going to have 1 minus n into n plus 2 divided by 2 multiplied by 3 a1. Then a4. That gives 2 minus n into n plus 3 into, sorry, divided by divided by 3 multiplied by 4 a2. Already there is a value for a2, which is what we have here, and that can be written as minus n into minus n plus 2. Then I have n plus 1 and n plus 3, all divided by 4 factorial a0, a5. So we substitute 3 here. We're going to have 3 minus n into n plus 4 divided by 4 multiplied by 5 a3, and there's a value for a3 that gives, let's write it as minus n plus 1 minus n plus 3. I have n plus 2 and I have n plus 4, all divided by 5 factorial a1. Now observe that the value for individual coefficients is alternating between a0 and a1. Let's generate two more values. One value for the even and the other value for the odd before we generalize. Now, following the same pattern, a6 becomes minus n plus 2 minus n plus 4 n plus 1 n plus 3 n plus 5 n plus 7, all divided by 6 factorial a0. While a7 becomes minus n plus 1 minus n plus 3 minus n plus 4 minus n plus 5 into n plus 2 n plus 4 and n plus 6, all divided by 7 factorial a1. Generalization now. For the even subscript, we have a0 as an arbitrary value. For the odd subscript, we have a1 as arbitrary value. So there are going to be two generalizations, one for even and one for odd. Let's go for the even first, 2k. How will it look like? Now, when we have 2 here, there are just 2 terms at numerator. When this becomes 4, we have 4 terms at numerator. When it was 6, we have 6 terms at numerator. There must be 6 terms. 1, 2, 3, 4, 5, 6. This is not here. Sorry about that. 6 terms at numerator. Now that we have it as 2k, there must be 2k terms at numerator. How do we generate all the 2k terms? Very simple and straightforward. Let's take the term one after the other. Observe again that there are two different types of terms here. The first one is this that has negative, while these are strictly positive. Similar thing happens here, negative, 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 and all these are positive. Now let us bring out all the negative. Here we are going to have two negatives, that is minus 1 raised to the power 2, minus 1 raised to the power 3. At this point it's going to be minus 1 raised to the power k. Then we are going to have n minus 2, n minus 4. It continues until I have n minus. Now let's look at the relationship between the subscript and the last term that we have. If you look at this, we have it after factoring out the negative, we are going to have it as n minus 2 as the last term, and what I have here is 4. What that one simply means is I have this one to be n minus 4 plus 2. When this is 6, the last term here after factoring out negative is n minus 4. So the relationship between that term and 6 is simply n minus 6 plus 2. So that means that the last term here will be n minus 2k plus 2. That's the last term that we have. Now let's consider the second part. The second part we have n plus 1, we have n plus 3, it continues. Is there any relationship between that subscript and the last term? Of course there is a relationship between the subscript and the last term. This is 3, this is 4, the difference is 1, this is 6, this is 5, the difference is 1. That means that we have what we have here, which is 6 minus 1, 4 minus 1, and that gives n plus 2k minus 1, all divided by 4 factorial, 6 factorial. Now we have 2k, it will be 2k factorial, and that's the generalization of the even coefficient. Let's go to the odd coefficient. In a similar form, the odd coefficient can be generated. And that gives a subscript 2k plus 1 equals minus 1 raised to the power k. I have n minus 1, n minus 3, up to n minus 2k plus 1 into n plus 2, n plus 4, up to n plus 2k, all divided by 2k plus 1 factorial. That is the generalization for the second coefficient, that is the odd coefficient. Now, the next thing, we now substitute all these coefficients into our trial solution given by equation 3. From equation 3, comma, we have y equals summation ar x to the power r plus c, r from 0 to infinity. Now, when c equals 0, when c is 0, then what do we have? So this becomes y equals summation ar x raised to the power r from 0 to infinity. Now observe, the coefficient of this is divided into 2. We have the even, we have the odd. So we can divide this into 2 by saying that this is summation r even to infinity ar x is power r plus summation r equals odd to infinity ar x is power r. By so doing, we can now substitute the coefficients. For the even, we are going to have it as a naught plus summation r even to infinity a sub 2k x to the power 2k, because that's the generalization term, plus a1, which is an arbitrary x, plus summation r equals odd to infinity a2k plus 1 x raised to power 2k plus 1. In fact, let us erase this. Let's erase this and maintain that. Then what do we have? We have a naught plus summation k from 1 to infinity. We have the general term here minus 1 raised to power k n into n minus 2 n minus 4 up to n minus 2k plus 2. Then we have n plus 1, n plus 3 up to n plus 2k, all divided by 2k factorial x raised to power 2k. That is the first one, a naught. That's the first one. Now the second one, plus. Now, erasing the first time here was deliberate so that I can explain what we have here. Odd numbers start with 1. If I substitute 1 into this point, I will have x raised to power 3. There is no x raised to power 1. So in that case, that means that we need to move out x raised to power 1 first, then we generalize the remaining one. And that gives a1 x plus what we have there. So that we have this as a1 x a1x plus summation k from 1 to infinity, the general term minus 1 raised to power k, n minus 1, n minus 3 up to n minus 2k plus 1 into n plus 2, n plus 4 up to n plus 2k. This is n plus 2k minus 1 generalization, all divided by 2k plus 1 factorial x raised to power 2k plus 1 a1. So we can now conclude that the first solution, y1, is a naught. The first solution, which is the same thing as Pn of x, can be written as, let me ignore this first. The first solution is a naught into 1 plus summation k from 1 to infinity minus 1 raised to power k n minus 2 n minus 4 up to n minus 2k plus 2 into n plus 1 n plus 3 into n plus 2k minus 1. That is the first solution divided by 2k factorial. That's our first solution. The second solution is y2 equals a1 into x plus summation minus 1 raised to power k n minus 1 n minus 3 up to n minus 2k plus 1 into n plus 2 n plus 4 up to n plus 2k, all divided by 2k plus 1 factorial, k